Welcome, y'all. This is the video to go over this week. Our next chapter we're kind of moving into a whole section is on analysis of variance, or Anova for short. So we're going to talk about this. Now, Anova, one of the first things to know about Anova is it's just a giant family of statistical tests. So there's not just one Anova. It really covers a whole bunch, and the point is to compare the means of two or more groups. Now, we've actually done this a few times when we've compared means of a sample to a population. We did this with the z-test, the single sample t-test. And then when we did two sample t-tests, we had the paired independent. And we even talked when we did paired that there was a limited amount we could talk about the effect without doing something like ANOVA. Now, ANOVA doesn't really tell us what is the effect, but it does help us know more about things. So it's really is designed to share, especially if there are two or more. This is a really, really good if you have more than two groups you're comparing. So if I have, like, for instance, three different groups I'm studying, I really want to see how that works out. Now, we're going to start with what's called between subjects one-way ANOVA. And I'll talk a little bit about what that means more about between subjects. That's what we're going to study next week when we come back to in-person on Monday. But in the meantime, I just want you to understand that we will also get to one-way repeated measures ANOVA. So again, notice the one-way, and between subjects two-way. So let's talk about what those terminologies mean. So first off, what does between subjects mean? Well, between subjects literally means that we are just going to have an extension of, it's going to be independent samples. So between subjects means we're going to just comparing between subjects the two samples. And this is the independent sample t-test. So the between subjects, ironically, is independent sample. That's what that actually means. So whenever you see between subjects, again, we're going to do between subjects one way and between subjects two way. So let's talk about what does that one way mean? Well, one way just means you have one variable, one factor. Essentially, I could have like one treatment concept. Two way means I have two categories or something else. So for instance, if my explanatory variable was gender, I'd actually have two levels or two ways, male and female. And this is kind of how this kind of goes on. Now, the explanatory variable, the variable that, remember, we have two variables. We have our explanatory variable, that's our input variable, and we have our outcome variable. So explanatory can either be a grouping variable, meaning how I group them, or it can be some kind of independent variable. Those are different concepts. It's the thing that's explaining the difference that's going on. Just to make that very clear. So explanatory explains why we're having a difference, and its impact is on the outcome variable. Just taking you back to remind you. So again, we're going to talk about how many levels and then one factor and so forth. It's really how many explanatory variables. So in this case, I had I misspoke. If we had two levels, male and female, that's two levels, but that's only one factor because gender is only one factor. What if I had gender and age as two different factors? Then that's going to be a two-way variable. And then that's where it gets kind of funky, is how do we group things, especially when we have multiple different factors involved in the process. This gets a little bit more gross and wonky. So let's talk for a second about why we even need ANOVA. Well, ANOVA is needed because it really is to keep that type 1 risk. The truth is, this is what we've been trying to do in all these things, is reduce the type 1 risk. The risk of rejecting the null hypothesis when we shouldn't. So we're trying to keep that at a reasonable level when we're comparing multiple groups. To kind of understand that, let's just look at a quick example. Suppose I have 5 different conditions. I'm testing medication, and so I have 4 different kinds of medication I want people to take. And I have a placebo in addition to that. If you don't know, placebo is really a dummy medicine just to see how your brain affects things. It's a common thing that we use, especially when we're testing medicine effects and other things like that. It's really funny. Placebo effects is dramatic. Anyways, if I had this, if we group these in pairs, we would actually end up with 10 different pairs if we grouped all the different groups together. I would have, in essence, I'd have medicine 1 versus medicine 2, medicine 1 versus medicine 3, medicine 1 versus medicine 4. So I have those, and then medicine 1 versus placebo. And then again, I do medicine 2, but if I compare it to medicine 1, so I got to compare it to medicine 3, medicine 4, medicine 5, and the placebo. You keep going through that process, you count out there's 10 of them. So actually, there's two things I could do here. One, using t-tests, I could literally run 10 different t-tests. That is really, really annoying. I don't want to do that. It's a lot of different stuff I'd have to work through. So instead, we can use Anova. It makes it simpler. In addition, the more important reason we use Anova isn't just because it's tedious. With all those different pairs, there's actually a 50% chance that one of those tests actually has a type 1 error, even if my alpha level is 5%, 0.05. Even in that situation, so even if I use my T critical value of alpha equals 0.05, I still actually have a 50% chance. Notice that's a really, really big alpha, actually, chance of having a type 1 error. And this is what's called a runaway alpha, because I have so many tests. As you have several different tests that are all running together, it actually increases the probability of a type 1. So we don't want to do that. So not only do we want to compare all of them together, we want to be able to kind of figure this out. So what Anova does is it compares all of them at one time and tells me if any two of them are statistically different. That's really kind of nice because it takes all this and makes it one thing. However, if I do find that something is statistically significant, so that means that at least one pair is different, and that's important, then I have to perform a second test called a post hoc test. This is a follow-up test that's specifically designed to keep, again, the alpha really low and so forth. And it kind of depends on what some things happen. So we'll talk about a little more about these, but just know that we always start with Anova, because if Anova doesn't work, there's no need to go into the post hoc test and do even more. This is just a quick way to run through the process. So that kind of gives you an idea. So we need Anova because it just is another strategy to avoid making an error in discarding our null hypothesis when we shouldn't. So what exactly does it do? This is kind of a fuzzier question because there's some things, but let's just kind of explain the general idea. So it works by pretty much analyzing scores and the difference between the variability in scores. Now, variability is caused by a lot of things. One of the most common causes of variability is within group variability. Now, within group variability, a score is different. That let's say I have a bunch of people. Let's say I have a bunch of people in this class, and I use a different teaching technique to see how that will affect you. Well, based on your different individual background, your personalities, a lot of different things, that's going to have a different effect. So I could have two classes, one class where I don't implement the intervention and one where I do. However, within those classes, there's massive differences between the individuals in the classes. So that's within each of those groups, there's going to be some variability. And then we can talk about between the group, which is the variability due to the treatment that we're actually doing. This is the more interesting one that we really want to care about. However, we do need to talk about between group, we do have to talk about within group, because what if the between group is really being caused, what looks like between group is actually being caused by within group. We'll get to an example, kind of talk about it. Now, this between group, notice it's due to differences in the treatment. So this effect caused by the treatment is what we call the treatment effect. By the way, all these names hopefully make sense. Within group variability is the variability within one group of people. Between group variability means if I take the two groups, how do they compare to each other? It's really how their variance between them. And the treatment effect is looking at the impact of our outcome variable based on the explanatory variable. Now, between group variability, I mentioned, is actually based on two things: individual differences and treatment effect. Now, remember, within group variability is based on individual differences. So between group variability also has individual differences plus the treatment effect. So let's just look at it. I have an example here to see how we actually use variability and how that affects. So we have, first off, this in the top of these two designs, I have a visual where I have 3 bumps. These are 3 groups in experiments. And I have the means. Now notice, I'm going to get myself something to annotate right here. This first one, the mean for 1 is actually lies within the second group. So I'm trying to highlight, as well as mean 3. So it actually turns out that all 3 means, 1, 2, and 3, are within that middle group, whatever it was. That's kind of and depending on how much they overlap. Again, how much they overlap, because remember we drew these things, and these are pretty normal curves in and of themselves. When we look at these things, because they may not fall in the rare zone where the mean 1 and mean 3 are compared to the middle group that has mean of 2, a mean 2, it actually might not be significant. In this case, actually, if we went through the process, it wouldn't be statistically significant. But this is what helps you start seeing that there's enough overlap because of the individual differences here in this group. That's the variability of it. It actually could have happened that all 3 of these were just happened because of individual differences. However, we look at this bottom example, you can quickly see that they're very, very clearly 3 distinct groups, which means their treatment had an effect, significant effect that we were measuring. Even though there's variability within them, like we could have even had these 2 overlapping a little bit here, overlapping a little bit right here, and the means would be so far apart from each other. It is very, very clearly not. So this is where Anova actually uses variability to kind of visualize and see these things. So Anova, what it does is it actually compares the between group variability and the within group variability. And this causes a ratio that we call the F ratio. F is based on the statistician who came up with this. I just lost his name. It's in your book. But it's just an F ratio. And what it does is we literally calculate what is the between group variability, and we divide that by the within group variability. But again, between group variability is based on our individual differences and the treatment effect, whereas within group variability is only based on treatment effect. So thus, we can change this formula to be this, and that should be variability. I now see that I missed a Y. But the variability due to treatment effect plus the variability due to individual differences, and it's not really plus, by the way, it's just kind of, I'm trying to illustrate something, divided by the variability due to individual differences. And that is where we kind of get into kind of this funky spot. So this variability ends up actually having a massive impact overall. Now, so we're going to calculate this. We'll get into more about how to calculate this, the actual details, but I want you to understand this difference. But let's talk about what that ratio actually means. So this right here is a visualization of its distribution. As you can see, and this is one where they're showing when alpha is 0.05, then it has a certain thing and so forth. But the idea is you can see it has a peak at about 1. The reason for that is the mode, the most common value in the F ratio is actually 1. And notice it goes down to 0, but it doesn't go negative. And we'll talk about that. And that's just basically because of the variability. So where does 1 happen? Well, if there is actually no treatment effect, so the treatment doesn't do anything, then going back just a couple slides, if there's no treatment effect, then we have just the variability of individuals over the variability of individuals, which really means it's 1. So this is the key thing, that if I have F equals 1, it means there's absolutely no treatment effect. Further, As the effect of the treatment gets bigger, the numerator will get bigger. And thus the ratio will get larger than 1. That's all of this area right here. All of this will start growing out and just being more significant. And finally, because again, I said this before, but because variability is never negative, the F ratio is never below 0. At 0, technically it can be 0. It's not very common. 1 is the most common, and we just kind of deal with that. So I hope that kind of sets you up to understand how this works. Go ahead and just look through this. If you want to start looking at sections 10.1 and 10.3 about how you actually calculate this, you're welcome to do so. We're going to get into that again on Monday. That's the 28th. Sorry, I had to think about what day on the calendar is. But we will go over this a lot more. This will be our next major area to kind of deal with and talk about and help you get a little more familiar. Good luck.